Hello everyone, we're at a Planetary Surface Technology Development Lab at Michigan Technological University, and we're here today to talk about development of the NASA Big Idea Challenge T-REX Lunar Infrastructure Mission. This project was made possible by the hardworking members of our team, some of whom have already graduated, but you can see most of us in the following presentation. The Artemis mission aims to get the first woman and next man back to the lunar surface in a sustainable manner. Part of these missions include the extraction of water ice from the lunar PSR regions. Though to operate and extract significant quantities of water ice in these regions, it means that we'll have to operate in extreme environments for extended amounts of time. This means limited power generation and sometimes not having access to line-of-sight communications. This means that an intermediary step to relay power and data to missions within the PSR is required. Power and communications requirements make small missions difficult to do due to limited capability. So to maximize science and potential and operational capability of long-duration PSR missions, precursor communications and power architecture must be established beforehand. And further, during manned operations on the moon, a resilient communication architecture will help ensure the safety of astronauts. To solve this problem, we propose the Tethered Permanently Shadowed Region Explorer, or T-REX for short. T-REX is an infrastructure technology demonstrator mission whose goal is to provide reliable power and communication to other operations within the PSRs of the moon, where conventional line-of-sight communication and solar power generation is limited. This then decomposes into two mission objectives for us. First, that our mission should be able to power itself while in the PSR from the Eclipse lander that is deployed from. Secondly, it should be able to give power and data to other missions operating within its local PSR vicinity. The concept of operations for a T-REX mission is as follows. After touchdown, T-REX will then perform a systems checkout and egress from the Eclipse lander via a ramp or similar method. During this egress, the rover then starts to deploy its conventional tether behind it, and the rover is normally operated via commands issued from an Earth-based ground station and sent to the Eclipse lander via the Deep Space Network. Next, the T-REX will traverse from lander towards the rim of a PSR. While, according to this competition, we have a nominal 125-meter distance from the PSR crater, 250 meters of conventional connecting tether is allocated for and the T-REX rover to account for deviations from the direct path to the rim. Next, from this point forward, the T-REX will then start to descend over the rim of the PSR crater and begin descent. Upon reaching a sufficiently shaded region, the rover will then stop its movement until the primary spool has reached a cryogenic temperature that will allow power transfer by the superconducting tether that the T-REX rover will start to deploy at this point. This primary spool holds a 2-kilometer-long multi-channel superconductor, or SAT for short, and after traversing down up to the 45-degree download slope, the rover will then park at a relatively flat region at the PSR basin. T-REX will remain in the PSR, acting as a power and comm sub for other missions within the PSR. A coupling interface then provides power to any rover which docks within the T-REX rover itself. After recharging is complete, the client rovers can then detach and continue on with their missions. Communications between the PSR and the T-REX and the client missions are performed using a full duplex RF communication system. Two-way communications is then established from Earth to the client mission via our mission. This demo mission is expected to last 1 lunar cycle or 12 to 14 Earth days, but can last longer dependent on if the Eclipse lander is able to survive the lunar night. We followed the systems engineering process when developing our framework and mission architecture. Our mission was decomposed into requirements separated by subsystems and recorded within the Requirement Verification Matrix, or RVM. The RVM is written from the point of view of a flight mission, and requirements in this RVM have 2 verification gate stages, green and yellow for flight and engineering models requirement verification respectively. This gives us the granularity to show real progress towards engineering models developed for BIG while keeping T-REX in the context of an actual flight mission. Our team structure is then organized per subsystem. People in each subteam are responsible for verifying and documenting their own requirements and come together during system integration. This process from developing components to testing the entire rover can be seen in our current timeline, which is updated bi-weekly and accounts for external delays.
Our team used many different facilities to develop a prototype version of T-Rex. Two key facilities in our lab are the Simulant Sandbox and the Dusty Thermal Vacuum Chamber. The Simulant Sandbox with gravity offloading capability was created in the PSTDL, and 5,000 kilograms of simulant was manufactured at Michigan Tech. Simulant was made by crushing glassy black scoria from a New Mexico quarry and mixing it in an optimal ratio with pre-crushed anorthite from a quarry in Greenland. This resulted in an accurate lunar Highland mechanical simulant with a reasonable mineral composition. The lunar simulant has very fine sharp particles and a tiny fraction of respirable silica requiring the use of HEPA filters in the negative pressure enclosure, as well as PPE with N95 filters and respirators. The simulant was placed in the sandbox and lunar analog terrain was created with rocks and craters, as well as a 45-degree slope. The Dusty Thermal Vacuum Chamber, or DTVAC, is connected to a liquid nitrogen tank that cools an internal thermal plate and shroud down to minus 196 degrees Celsius and can also be heated to as high as 150 degrees Celsius. A roughing pump and turbo pump are connected to the DTVAC via an industrial air filter and can achieve 10 to the minus 6 torr when empty and 10 to the minus 4 torr with lunar simulant and ice present. This facility lets us conduct tests of robotic systems in a simulated lunar PSR environment, accounting for temperature, pressure, and regolith. The DTVAC facility at Michigan Tech is planned to be operational by the end of January 2021. It will be used to conduct tests of the Mark III T-Rex prototype once commissioning is complete.
The T-Rex rover is composed of the following major components: a conventional conducting tether, used for a power and data link while traversing outside of the PSR, a conventional conducting tether spool, used to unspool our initial tether via tension and to eventually act as a thermal break between the tether in the illuminated lunar region and the superconducting tether in the PSR, a superconducting tether, used for a power and data link once we were within the PSR, a tension measuring system, used to measure the tension in the superconducting tether to provide information to the unspooling system, a passive hot dock power coupling, used to provide power to compatible rovers with the appropriate active end, a front-mounted sled in order to control our descent down steep crater edges, the rover chassis, containing the electronic stack, motors, heaters, and insulation to keep everything shielded and sufficiently warm during the traverse in the PSR. Within the rover, there are brushless electric motors which drive the wheels, the previously mentioned electronic stack, containing components such as onboard computers, power distribution boards, internal sensors, and wire harnessing, the spooling motor for the superconducting tether, which actively unspools the tether at a rate determined by the tension measurement system in order to keep a safe tension in our tether, a slip ring between the power system and both tethers, allowing us to avoid running power through our superconducting tether before it has been able to cool down to its appropriate operating temperature. And finally, decoupling motors, used to drop the conventional conducting spool and release the slip ring. This runs power through both tethers to the power system when the superconducting tether has reached the appropriate temperature. All of the components in the T-Rex rover are grouped together by overall purpose into 7 different subsystems. Command and data handling, providing overall system control and data collection through its flight software. Spooling, controlling the spooling operations of both the super and conventional conducting tethers. Communication, handling the connection between our system and other wirelessly connected rovers to the ground over our tether. Vision and mobility, providing the drive motor control and camera feeds. Electrical power system, providing and regulating power to all onboard electronics. Tether, the operation of both of our tethers to provide a link to the connected lander. Lander, consisting of any hardware necessary onboard the connected lander. And finally, structures, consisting of the mechanical and structural backbone of the T-Rex rover. The makeup and operations of each of these subsystems will be explained in the subsequent sections of this presentation.
One of the most unique features of our design is the use of a superconductor in our tether. The superconducting element is significantly lighter but more fragile than its conventional counterpart, and special considerations need to be made to ensure the superconductor stays within its proper operating conditions. These conditions are reflected in our RVM and include keeping the tether at its proper operating temperature of 92 Kelvin and below, keeping the tension in the cable less than 5 newtons, and making sure the tether does not exceed its minimum bend radius of 1 centimeter. The spooling assembly, or SPA, within the rover ensures these requirements are met. This figure highlights the path of the tether through the rover, starting with the red conventional conductor, or CCT, coming from the lander, which is stored on the CCT spool. The tether is connected to a green slip ring, which is attached to the superconducting tether, or SCT. The SCT goes through the tension measurement system, or TMS, and eventually to the SCT spool, which is connected to a second blue slip ring that delivers power and communication signals to the rover. The first 250 meters of the tether is made of a conventional copper conductor. This is done to span the gap between the lander and the crater, an area that experiences temperatures which are higher than the 92 Kelvin operating temperature of the superconductor. The SCT spool acts as a method of deploying the conventional conducting tether and a heat break between the sections of the tethers once deployed. The SCT spool is driven by a motor coupled to its shaft. This motor can reel in or release the superconducting tether based on the position of the central pulley in the TMS. Currently, the TMS uses an analog device to measure the displacement of the central pulley. The 10-bit integer that it outputs is used in conjunction with the velocity profile seen in the figure to the right to define how fast the SCT spool should be rotating and in what direction. Of the two velocity profiles that we experimented with, we found that a parabolic profile worked well to reduce noise near the tension set point and was still able to quickly respond to fast accelerations. The video playing now shows a portion of our slope testing and the TMS managing the tension in the tether. Note how when the rover slips on a loose regolith, the spool quickly releases the extra tension generated from the fast acceleration. Two types of tests were conducted with the SPA inside the sandbox. The first being a flat ground test, which was used to get data on obstacle traversal and TMS accuracy. Once the accuracy met mission objectives, we moved on to slope testing, where we proved that the system can continue to perform on a 45-degree downhill slope. The two charts on the right show the tension measured by the TMS and a force gauge as a reference. As you can see, the TMS was able to keep the tension well below the 5 Newton maximum and was accurate within half a Newton. Moving forward, our main objective is to conduct more realistic tests using a live tether in lunar conditions. To get there, a number of design and hardware improvements need to be made, including using cryogenic and vacuum-grade components, as well as making a few modifications to the SCT spool and TMS pulleys to accommodate the wider multi-channel superconductor.
Once entering the PSR, the T-Rex begins its pre-descent cool-down phase, where we wait for the superconducting tether to cool to 92 Kelvin, also referred to as its superconducting state. During this period, the conventional tether spool acts as a thermal buffer between the end of the conventional conductor and the beginning of the superconductor. Through simulation, it was determined that using the spool as a radiative heat sink and thermal break increases heat dissipation of the tether, reducing how far into the PSR we need to travel before beginning the cool-down phase. Future testing will take place in our DTVAC to validate the effectiveness of this configuration. The other main source of heating that the superconducting tether will experience comes from within the rover. The motor driving the superconducting spool is the main source of this heating, as the motor shaft provides a direct path for conduction between the electronics we want to keep warm and the tether. To simulate this, a model was made to analyze how quickly radiative cooling could bring the superconducting spool to 92 Kelvin with the heat load acting as the motor. By using a fiberglass composite for the motor shaft, MLI blankets, and anodized aluminum for the spool, the tether is projected to reach its superconducting temperature after 2 days. Verification testing in the DTVAC will be used to test the validity of this model.
The COM subsystem serves to provide data transfer between nodes in its wireless local area network, including internal rover and external client communications. The tether deployed by T-Rex provides the medium for lander-rover data transfer, which consists of 250 meters of conventional conducting Cat5 twisted pair, followed by 2 kilometers of superconducting YBCO cable. Driving the subsystem are an integrated Ethernet switch, the main onboard computer, and any active ground control software instances. The T-Rex COM subsystem utilizes the WebSocket network protocol to communicate with external nodes. This protocol was selected as it provides a useful abstraction over base TCP sockets, including features like automatic message framing, heartbeats, and more. This protocol allowed the T-Rex team to accelerate the development of the COM subsystem by relying heavily on its feature set. The VDSL2 standard was chosen as a modulation scheme for communication over the tether. VDSL2 provides full duplex communication, low latency, and an adaptability to various RF noise environments. The implementation of this modulation scheme provides data rates that are above that of the Deep Space Network. Earth to T-Rex communication speed will therefore not be limited by T-Rex hardware, and this technology can scale easily to meet growing data transfer needs on the Moon. The focus of comm testing has thus far been centered around tether functionality, in which several key requirements have been verified. A test of the communication functionality of the conventional conducting tether revealed that it was possible to transmit images with an average size of 200 kilobytes via VDSL2 over 305 meters of Cat5 twisted pair. When implemented on the T-Rex rover, the conventional conducting tether is able to reliably handle data transfer, including video streaming at 720p resolution at 30 frames per second. Subsequent tests of parallel one-channel sections of superconducting tether were then performed. While submerged in a liquid nitrogen bath, a length of approximately 0.3 meters, a superconducting tether had the ability to maintain a VDSL2 link, performing several ping tests with no packet loss, and eventually allowing for video streaming at approximately 30 frames per second and 720p resolution.
The T-Rex electrical power system, or EPS, takes the incoming power from the tether, steps the voltage down, and distributes it to the various subsystems on the rover, while collecting power and state of health telemetry. The EPS firmware flashed to the onboard Arduino Nano is designed to act predictably with the intent of it being the last system to fail on the rover. Written in the Arduino language, the firmware periodically reads values from each of the 5 current sensors. These values are then relayed to the ground station to be displayed. The hot dock, provided by Space Application Services, is the electrical mating interface used by the T-Rex and is capable of transferring up to 40 amps at 100 volts to client rovers. This coupling device was chosen for use on the rover due to its ability to handle large misalignment tolerances as well as its secure locking mechanisms to ensure a solid connection. Further testing of the hot dock's interfacing ability will take place with and without dusty vacuum conditions. After exiting the CLPS lander, the rover will deploy up to 250 meters of conventional conducting tether and 2,000 meters of superconducting tether over the course of its mission. The CCT will be constructed out of 16-gauge copper wire with a resistance of 13 milliohms per meter. The SCT, while at cryogenic temperatures, exhibits a near zero resistance. Adding the loss along each section of tether results in a total resistance of 3.25 ohms across the 2.5 kilometers. The power budget for this mission is divided up into 3 modes of operation: moving, cooling, and parked within the PSR. Using data drawn from each component's datasheet, an estimate of the average and peak power for each mode can be determined. The rover will draw on average 40.5 watts during Mode 1, 23.3 watts during Mode 2, and 19.5 watts during Mode 3. Note that these values are significantly higher than that was originally requested, but are in the operational range of the CLPS lander. Further testing and design iterations will focus more on the efficiency and DTVAC readiness of the hardware. Our team conducted mobility tests inside of the sandbox to evaluate how accurate our power budget estimates were. We recorded a power draw of 33.6 watts in Mode 1, 18.1 watts in Mode 2, and 14.4 watts in Mode 3. During these tests, heaters and lights were not used. If heaters and lights had been used in the tests that required them, then the additional amount of power T-Rex would draw is very close to the power budget estimates. The T-Rex will traverse from the CLPS lander to just inside of the PSR, where it will wait for the SCT to cool below 92 K. During this traverse, the rover will operate solely off of battery power, for a worst-case scenario where the CLPS lander cannot provide enough continuous power. Note that larger CLPS landers can supply much more power, which would allow for a much smaller battery. Since the conductivity of lunar regolith is extremely low, we do not need to worry about the exposed copper plating of the SCT shorting. Due to their topography, the PSRs will possess a large negative charge due to the deflection and absorption of solar wind plasma. Further testing is needed to determine the effect of how these electrostatic potentials will affect the SCT, as well as the rover electronics. In addition to charges built up by solar winds, objects moving through lunar regolith will accumulate a charge due to the triboelectric effect. This will also require future testing to ensure the rover's electronics are not damaged. EPS has been tested continuously throughout the development of the rover, at each stage measuring the output of the voltage converters, as well as testing the current sensors to ensure they are correctly calibrated. The firmware has gone through several iterations, and each time tested that it successfully integrates with the OBC and CDH. Moving forward, the focus of EPS will be to improve the efficiency of the system and ensure it will survive the environmental conditions of the DTVAC for future testing. Testing will be done with the SCT and rover electronics to help mitigate the effects of the electrostatically charged regolith and the triboelectric effect.
T-Rex will be remotely controlled and will require a vision and lighting system. Our prototype version of this system uses a 5 megapixel camera and a 3-watt LED. To test the effectiveness of this system, our team conducted mobility tests in the Simulant Sandbox in both light and dark conditions. Results from these tests showed that the system was effective for distances up to 2.4 meters away and that a rover operator could navigate using only the camera video feed. The path forward for a flight-ready version of this subsystem will involve slight modifications to the hardware design and selecting an upgraded light and camera that can be used inside the Dusty Thermal Vacuum Chamber. T-Rex's mobility system uses brushless DC motors with gearboxes. The motors were sized based on results obtained from a force balance study that looked at 4 driving scenarios. From these calculations, we determined motors with an output of 2.5 Newton meters would work for the prototype T-Rex. However, when we tested these motors on the rover, we soon realized they were undersized. Every time we attempted to drive over a rock, the motors would trip on an overcurrent protection fault. To solve this problem, we reevaluated our calculations and added a larger factor of safety for torque. The second set of motors we purchased were larger at 30 Newton meters each, and this proved to be more than enough power for our tests. After installing the new motors, we experienced 0 issues from that point on with mobility testing. Currently, the motors installed on T-Rex are not space rated. The path forward for a flight-ready version of this subsystem will involve selecting motors of similar power but that are space rated and can be used inside the DTVAC.
The software developed for the T-Rex has been designed for portability from one hardware prototype to the next and into a flight model. The control software has been written from the ground up specifically for the T-Rex. The primary goal of our ground control software was to provide a single access point to view telemetry and provide system control while keeping in mind the latencies of the deep space network. By embracing web technologies that have flight heritage in our software, we were able to accelerate our development pipeline. While providing all necessary functions, we were able to keep our ground control software light and manageable at just around 3,000 lines of code. Using these technologies, we gained the ability to control the T-Rex from any computer with an active network connection. We found it extremely beneficial to develop certain subsystems on board the T-Rex with these technologies in mind. As both sides of our software were written in the same programming language with the same feature set, we were able to work on various parts of the T-Rex in parallel. Employing a very popular networking protocol found in web technologies, we gained many useful features and could abstract away many complexities of network communication to focus on the development of the T-Rex. We are satisfied with the choices we have made in regards to software design on the T-Rex. Commands passed throughout subsystems operate with the speed and reliability we designed for. As we look towards a flight model for the T-Rex, we plan to change a few items. Moving forward, we plan to integrate high-resolution camera streaming into the T-Rex with multiple parallel camera feeds instead of our current single camera. Software on the T-Rex has been developed in a way to mitigate rewrites and redesigns as we move forward to a flight-ready model. Further improvements are planned in our software pipeline to integrate with the robot operating system and future graduate research at the PSTDL. With the addition and integration of autonomous gravity offloading developed by our team and provided by the PSTDL Sandbox, the T-Rex can be put through harsh mobility testing to simulate the worst environments possible on its mission into a permanently shaded crater.
The frame of the T-Rex is constructed out of aluminum, which consists of several components. The main structure consists of a top and bottom plate connected together with standoffs. Attached to the sides of the standoffs are side panels that add to the rigidity of the structure. The frame panels use laminated isogrids to reduce the weight while keeping dust out of the rover. Another dust preventative feature is the use of dust guards that prevent dust from falling off the wheels onto the top of the rover. Flight-ready versions of T-Rex would also use a variety of other features for EMI and EMC mitigation, and installing multi-layer insulation for better thermal control. Additional refinement to their structure will be done based on the shock and vibe requirements levied by the launch provider. The wheels of the T-Rex rover use grousers to provide adequate traction needed to control the rover while traversing PSRs. The wheels used on the most up-to-date prototype are fully 3D printed from PETG plastic. The use of 3D printing made manufacturing the wheels much easier and allowed for a much more complex design. The wheel design is not our primary focus and was designed out of necessity for functionality testing. The third point of contact for the rover is the front sled. Although using a sled seems unconventional, there are several reasons for its use and placement. Using a sled instead of a wheel provides a few key advantages for the mission of T-Rex. For one, a large portion of its mission will be traversing down steep slopes into PSR craters. It was found that the sled provides much more control when driving down slopes than, say, a wheel. A wheel does not provide enough resistance to help keep the rover in control when on the slope. There is also good reason for the sled being located at the front rather than at the rear. Having the sled at the front allows for more stability when traveling down the hill because the location of the sled allows the CG of the rover to be in front of the axles. Having the CG in front of the axles allows the rover to have a self-righting effect caused by the moments induced by gravity, which point the front of the rover down the slope. Having the sled at the rear presents danger of the rover flipping around while trying to descend. It was also found in our testing that driving with the sled in the rear was more difficult and caused traction issues when driving on flat and inclined terrain.
During this competition cycle, our team has made significant progress towards raising the technology readiness level, or TRL, of the T-Rex rover. The goal is to reach TRL 6 by April 2021. From proof of concept testing, we have shown that we can deliver power and data over a superconducting tether. We then developed a prototype moon rover capable of deploying this tether from flat and inclined terrain. We have then produced and finalized atmospheric and vacuum testing facilities from scratch to conduct all of this work. There is a clear path to flight for our technology. While there are hurdles to make the system space-rated, there are no real showstoppers. The hardest problem was integrating the hardware and then waiting for it. It always is. Now that everything talks to each other, it comes down to iterative testing and improvement. Recently, we have adopted an agile approach to development as of late December to speed up our testing and development cycle. Builds will be released bi-weekly in sprints, and during these cycles, lower fidelity components will be switched out with higher fidelity versions until we have a vacuum-compatible Mark III rover, a ship of Theseus of sorts. After vacuum testing of Mark III is complete, we'll do a similar process to building a flight model, and whatever form that technology may take. We plan to continue development after Big. Our rover is uniquely positioned to perform the task for the Watts on the Moon Centennial Challenge, with only minor modifications required. Should we be selected for the first phase, our lab would partner with industry to provide a more robust solution for Phase 2 of the Centennial Challenge. We are open to inquiries for partnership opportunities from NASA and industry which incorporates technology at this time. NASA Big Idea Challenge has given us all the experience in this niche field and facilities to test more missions in the future. Several people on our team have even decided to pursue master's and doctorate degrees inspired by work on T-Rex. Thank you for listening to our presentation. We are excited to continue development and testing of our rover and hope to see our technology and facilities supporting our missions in the near future.